Have you ever reached that point where everything works, but then you just want to add one more thing, one more button, one more sensor, and there's no more space? I've been there plenty of times, and today we're going to fix that properly by moving all the button inputs off the microcontroller without changing the rest of the project. Welcome to more Little Man Builds. So before we jump into the code, let's talk about this little chip we're using here, the MCP23017. What it gives us is 16 extra input or output pins over I²C, which means with just 2 wires, the SDA and SCL, we suddenly have a whole extra bank of buttons and switches without burning through the ESP32's GPIOs. It's fast enough for real-time user input, and it supports hardware pull-ups, just like the microcontroller does. On top of that, it has 3 address pins, which means you can put up to 8 of these chips on the same bus. So in theory, you could scale this up to 128 inputs using the same 2 wires. By the way, this chip does have interrupt pins that can wake the ESP32 when something changes. We're not using them here because for buttons, simple polling is more than fast enough. But if you have ultra-low power or massive input bank requirements, interrupts definitely make sense. So with that in mind, let's look at how we wire this up. So as always, we've got our ESP32 and for this example, an MCP23017 and 3 buttons. Firstly, we set up a common ground, so everything shares the same reference. All of the button pins are configured as input pull-up, which means the pin normally sits high, and when you press the button, it gets pulled down to ground, and that's what we call active low. Because of that, one side of every button is connected straight to ground. The MCP can run at 3.3 volts, so we power it directly from the ESP32's 3.3 volt pin. Next, the 2 most important wires, I²C. GPIO 8 on the ESP32 goes to SDA, and that's the data line. GPIO 9 goes to SCL, and that's the clock line. So here, A0 is test button 1, A1 is test button 2, and B0 is test button 3. Notice that we don't need resistors here. The MCP handles the pull-ups in software, so the wiring stays clean and simple. Just a quick note, this video builds upon the base universal button library logic, so to ensure you have the full picture, I'd highly recommend watching this video first. At the top, we still define our buttons in the same way. 3 logical inputs, test button 1, 2, and 3. But notice the comment, when you're using a port expander, those numbers in the mapping don't correspond to physical pins. They're just unique keys, so the library can identify each button. We'll come back to this in a moment. Next comes the real hardware mapping on line number 24. This is the important link. The button names or the intent is now linked to each MCP pin. So test button 1 maps to A0, test button 2 to A1, and test button 3 to B0. The static assert is just there to ensure that if you add a button and forget to update the array, the compiler catches it before you ever flash the board. Timing is still centralized, debounce, short press, long press. There's 1 config struct up front and no scattered magic numbers in the loop. Next, we inject a custom reader function. The handler asks, is the button pressed? And our reader answers by pulling the state from the MCP over the I²C bus. The line index from key is how we translate the button key into an index in our mapping array. If it's one of the configured buttons, we read from the expander. If not, we can fall back to a digital read on the MCU pin. And here's the key point. This library does support hybrid setups, but you have to be a little bit careful. Let's revisit the mapping point from earlier, but create a new example where we add an extra button. So we've defined a button list, but now we're adding test button 4 to pin number 9. Let's say you forgot to update the expander mapping, so within the MCP array, we still only have 3 pins, 0, 1, and 8. Now we have 4 logical buttons, but only 3 physical MCP pins. So what happens to button number 4? Let's revisit the function. It has nowhere to go on the MCP, so it drops into the fallback and is now being read as a GPIO from the ESP32. By the way, this is completely legitimate and you can intentionally do this with this pattern, but that's why for this sketch I added the static assert as a bit of a safety check. So here's a rule you can use. When using an MCP23017 in this pattern, think of the button number as a name and the MCP array as the address. My ultimate recommendation is to leave the numbers weird and ugly and avoid making them look like pins. Moving on, so now we build the handler with make buttons with reader, and we tell it to skip pin init because these pins aren't on the MCU, and we'll configure the MCP ourselves. In setup, we bring up I2C, start the MCP at address 0x20, which is the default, then configure each MCP pin as input pull-up. This is the same electrical behavior as a normal button on the MCU. When pressed, it reads low. The loop is the same pattern, just asking each logical button for an event, short or long. So let's look at the project in real time. We have a short press on each of the buttons. And there's the long press. So in summary, buttons can live on the ESP32, on an expander, or even on something wireless tomorrow, and the rest of the project doesn't care. This is what clean architecture looks like in embedded. Inputs are abstracted, events are consumed, and the hardware details all stay in one place. This is where we left off, and it's our visual model for the whole car. Input, decision, and execution. On the left, we've got buttons and the RC receiver. In the middle is the control core where the intent and safety rules live, and on the right is the motor driver doing the actual work. Now we want to make that more concrete, so our buttons and remote control become publishers. The button publisher handles debounce and timing. The RC publisher handles remote control decoding and failsafe. They both push clean data onto the button bus and RC bus respectively, so the control core isn't reading pins, it's only reading intent. Next we move the buttons off the ESP32. The MCP publisher talks to the port expander, checks its health status, and publishes into MCP bus. From there, the button publisher still produces the same button bus events, so nothing downstream needs to change. Lastly, we add authority. The authority bus decides who's allowed to drive right now, the RC, pedals, joystick, whatever. When inputs conflict, authority resolves it before any commands reach the motor. But this is already a huge change or refactor, so we'll build the authority router out properly in later episodes. For now, the big idea is events in, policy in the middle, and controlled outputs at the end. That separation will keep the system scalable and safe. So with that in mind, let's continue with the car development and crack on. Welcome back, and before we add the port expander, I want to clean up the shape of the project, because if I add more hardware into an already messy structure, the mess will simply spread. The first part of this refactor is to ensure there's clear places for hardware facts, behavior rules, shared data, and safety decisions. So let's start in the config folder. We're going to create a new file called app.io. This will include all the GPIO data, addresses, motor or UART pins, logical mappings, and things like this. We'll start with a copy-paste. Now, instead of having everything all in one file, we can split it out piece by piece. We can move these sections into the I/O file. Now you might be wondering how I actually came up with the pin allocations in app.io.h, and the answer is I did not just pick pins because they were nearby. On the ESP32S3, some pins affect boot, some are used for USB, some depend on the exact module, and some are just better left alone unless you really know why you were using them. So before I wire anything, I always make a pin plan, and this table is from part 1 of my ESP32S3 stability manual. It is part of a larger stability series covering the problems that make ESP32 projects reset, crash, refuse to boot, or behave differently once they leave the desk. Part 1 focuses on hardware, power, boot, and pin planning, and you can grab that one for free at littlemanbuilds.com. You can find that link above, or you can also find it in the description. Next, we're going to create an app policy. All the timing values should live here, like debounce, long press, or anything that involves common units. These are not hardware facts, they are decisions about how the system behaves. Next, we'll implement a safety policy. So imagine you're driving and someone's giving you directions over a walkie-talkie. If they go silent for too long, you definitely don't want to keep driving. It's better to stop, and that's exactly what this code is doing here. For example, a frozen task could lock the throttle on. The car could keep driving if the remote was disconnected. So with this, every car failure mode means that the car stops. You could also think about it like a WhatsApp last seen. This file is to hold all RTOS information in one place. It removes a lot of the noisy setup code, but more importantly, it means task scheduling is now visible in one place, so I can look at this file and immediately understand which work runs on the I/O core and which work runs on the control core. We also have some task descriptors. This is the task name, stack, priority, and the core. We can now rename this file We can move all this code to a new section so it can be deleted. And all of these other configuration variables can also be deleted. Now we'll do a quick review of the utilities. I'm not going to spend too much of this video going into the detail behind each utility file, but I do want to give you a brief explanation as to why they exist. So the first one we'll call is button debug. Now it will generate an error because we haven't completed the bus upgrades yet, but basically this one is to move the button logging out of the control core so the diagnostics aren't cluttering the control policy. By the way, all of these files will be freely available on GitHub, so you can look at all the detail there. The next file we'll create is a clock.h. This replaces the scattered millis and ESP getTime function calls with one project clock. This ensures everyone agrees with what now means. This file replaces all the serial.print calls with debug helpers, and these can also be enabled or disabled. Liveness extracts repeated stale data checks. This makes the safety behavior consistent and handles timestamp wrap safely. The math functions file is to extract clamp and %normalize conversions. This prevents mixing 0 or 1 values with 0 to 100 values. Publisher is to extract the snapshot RTOS publisher startup. This means each publisher gets the same timestamp source, heartbeat policy, and task pattern. This simplifies the calls, and I'll show you how this works shortly. Task replaces the repeated xtask created pin to core boilerplate and centralizes the start task function. Now, officially, we should also change this name because they're not really libraries, it's more an application. So let's quickly rename it. We will be including a hardware abstraction layer as well. So let's also do that now. So the next important idea is that the system communicates using snapshots. A snapshot is just the latest known state at a point in time. That means that the control code does not need to know whether a button came from an ESP32 pin, port expander pin, or something else later. This is also how we'll eventually introduce the MCP23017, but we do need to first update our buses. We'll start with the RC bus. We will also introduce a buses file, so we can delete this part. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm, and I'd love for you to join our community. That's the rough template for buses, so we can now update the other files. And for this video, we'll add a direction command for the drivetrain. And I do apologize for the speed overviews. This video is already quite long, and I'm trying to strike a balance between explaining the important aspects versus allowing people to review the changes in their own time on GitHub later. I also understand that some of this refactor might be initially a little confusing, but I promise it will all make sense soon. Refactors are very common in embedded projects. The intent here is to make the hardware integrations in future videos easier to teach, hence why I'm doing all the naming changes. Now the button bus defines the logical button state, and the redesign should start to pay off. This also means that the button system can move between ESP32 pins or the MCP pins, but our control core architecture still reads buttons as accelerator, horn, left indicator, or right indicator, so the meaning did not change. So with that in mind, we should also now create the MCP bus and the authority bus. Think of this as a screenshot of all my switches. Instead of running back to the hardware every time, I take one picture and work from that. In this case, a 1 means not press because we're using input pull-up, which pulls the line high. When we press the button, the line is grounded, which is our on button state. So an F in binary is equal to 1111, an FF is equal to 1111, and that again. So this bit field represents all our switches from 0 to 7. If one of them was triggered, you would see a 0 in the field. Accordingly, FFFF is the whole group or the GPIO combined port section. So 1111 repeated 4 times. Now we can see the entire MCP state at any point in time. Lastly, for our architecture, we need an authority bus. Now this bus is all about who has ownership or control. Here are the authority sources for control access. We have a transitional state, one where the RC is in control. We have direct control at the car level, so the physical steering wheel and the accelerator, and we will eventually add in joystick control for disabled kids. So there's always an owner for each of the aspects of the car. This is the steering owner, which can have a default owner of none. And you can think back to the remote control where we introduced these different variables like power and speed, which can be controlled from there. So hopefully this will all start to come together over the next few episodes, where you can start to see how the logical inputs work together through this architecture to build a simple and safe car. Well, perhaps not simple, but definitely a safe car. We will build up the authority bus in greater detail, but there's already enough change for this episode. So for today, let's keep this simple. This file will act as a little helper to initialize the I2C bus before anything else. It's also a good example of separating hardware from application logic in case we need specific I2C functions later. We'll also create a new file called MCP230. Now the reason for this is because the button system reads from MCP230, not directly from the hardware. Buttons are still logical. An accelerator is still an accelerator, a horn is still a horn, but here only the electrical source changes, and this is the payoff by separating the meaning from the wiring. We're basically building a small adapter because the MCP bus only speaks raw hardware bits and the button system wants to know whether an input is pressed. This file converts between those two ideas. This also means the callback is kept clean. Otherwise, every button read would need to know or remember active low bit logic. So here the U means unsigned, which is safer and cleaner when we're doing bit level operations like masks and shifts. In essence, we're just looking to see whether there's an active low and if the logic has been inverted. Let's make a quick example saying bit equals 3. The masks would become this value, and this then checks whether the bit's cache state is low. That's the return here. Hopefully that makes sense. Now we need to create an MCP publisher. This is important because we need the publisher to own the port expander. It initializes the chip, configures the input pull-ups, samples both ports, checks whether the device is still responding, and publishes the safe default when it's offline. This will avoid the common pitfall where every feature reads the hardware directly. So if a button, switch, or future feature were to talk all to the MCP themselves, the I2C access would become really cluttered and harder to figure out. Instead, here we have one task owning the chip, and the rest of the subsystem can read snapshots from that. Now to the CPP file. And this is where we can start to use some of our utility functionality. So the MCP publisher samples the chip, then publishes GPIO A, B, combined pins, health, and timestamp. After that, consumers do not need to talk to the I2C directly. Let's quickly go through these methods. We try and initialize the MCP and see if it's healthy. We can then configure the pins only if it succeeds and reset the state on successful initialization. We can sample each of the members, but then still have a lightweight runtime health check to make sure that everything is still working. Then we have the one read per port and the presence probe or acknowledgement check. Now we need to have a look at the old state manager, but we should now be calling this a button publisher. So in the old shape, buttons were read directly from the ESP32 GPIO. In the new shape, the button handler gets a reader callback that reads directly from MCP230. That means the debounce system stays the same, the button names stay the same, and only the electrical source changes. In a lot of embedded code, dependencies are stored as pointers initialized to null pointer, which forces you to add checks and asserts everywhere just to prove the system is wired correctly. But here that dependency is mandatory, so I've switched to references to make invalid states unrepresentable, and this means the object cannot be constructed without its required dependencies. The compiler enforces this contract, so the defensive runtime checks can disappear. So the result is cleaner code that is more easy to reason about. The main architectural lesson is that if a refactor is done well, the change is just local, so adding the MCP to the system should not force the control logic to learn about I2C. I'm going to ignore these errors for now and come back to them. Now let's update the control core. So I'll add some pure policy level functions here that are not dependent upon the object state. I've intentionally kept them out of the class to avoid implying ownership or coupling. So having an anonymous namespace enforces this internal linkage and prevents accidental reuse outside. Again, now that we're using references, we don't need these asserts anymore. The control core reads the latest button snapshot, RC snapshot, and authority snapshot. It checks whether button data is fresh, and it returns throttle, horn, indicators, and direction. And so this section just gives me the latest authority state, and if it's unstable, just reuse the last good one so that the car never panics. The important thing is that the control core does not read hardware, it reads facts. That makes it easier to test, easier to reason about, and safer to extend later. Alright, so that's the control core updated. Almost there. Let's update the power drive handler. Now, I don't want to wait for exactly 0 here because electronics don't always hit a perfect 0. So we're waiting for basically 0, and that's why it's set to 1%. So the power drive handler consumes the resolved control command. It does not decide whether RC or buttons are in charge. That decision has already happened. Its job is to execute safely, check whether the control command is stale, clamp the throttle, ramp the output, and prevent sudden direction changes under power. Here we will implement something similar, now using the callback read, callback update, and callback OK functions. So let's replace this code. And finally, let's update the main.cpp. This section is to create all internal snapshot instances now before any RTOS tasks actually start. This avoids hidden first use setup happening later inside any running task. Now there's still an error somewhere here. Of course, we forgot to close the braces. I also want to go back through our app. The issue here was that buttons underscore was previously appointed to an object, but now it is the object itself. So instead of following an address with the arrow, we need to access the member directly with a dot. Let's double check everything else. I think there was still one issue with the MCP publisher and the power drive handler. So a constant is never going to work. That's a fail. This should always be able to be updated. Let's compile and see if there's anything else. Of course, brackets would help. Also, don't forget that we have to update our hardware from the test sketch we used earlier. So in this case, we're going to use B0 as button accel, B1 as the button horn, B2 as the button indicate left, and B3 as the button indicate right. Let's try each of the buttons. So there's our indicator right, our indicator left, our horn, the accelerator. And we can also press any of these at the same time, hold one over the other, and it always will record each press and press duration. Let's temporarily comment out this section. And let's bring in the debug from power drive handler. We'll save that and push this across to the ESP32 again. So this is our simple acceleration deceleration ramp. And that's what you can see here as I'm pressing the button and releasing. So everything's working as expected, which is great. Today we solved the just one more button problem by moving the inputs onto a port expander, but more importantly, we kept the architecture clean. The hardware changed, but the system still sees normal button events. This means that there's more inputs available, less GPIO stress, and a system that can scale without turning into a mess. All the examples from today will be available on GitHub, link in the description. Please also consider subscribing and smash that like button. See you in the next one.